Hi, everybody. Before we start Calculus 2 in a week, I wanted to share with you some thoughts about what is important from the Calculus 1 course you may have taken and try to get you in position so that you know what to expect in our first week of Calculus 2. So this first video is going to be about the concept of derivative and the way in which we pull those ideas forward into Calculus 2. And I'm going to emphasize one of the concepts from derivatives that causes a lot of issues for people at the beginning of Calculus 2. And that is the idea of derivative of a function. This is what you might remember as the chain rule. And I just wanted to go through it again real quick to talk about why the chain rule is true and the way that we can use it, and then kind of a shortcut for you. The reason that's important is because one of the first integration techniques that we do is to basically work backwards in the chain rule. And so if you have the right understanding of the chain rule, then working backwards will be easier. So we'll start with an easy example of a function that is just a compound expression squared, and we want to find an algebraic formula for f prime of x. And again, we're going to be using the chain rule, but I'm going to review where the chain rule comes from, and then see how we can use it. So it's not a hard question. We could just multiply out using FOIL 5x plus 3 times 5x plus 3. That will lead to this expression if we expand it out, and then the derivative should just be 50x plus 30. So the 2 comes down to the 25, this power goes down by 1, derivative of 30x is 30, and the derivative of the plus 9 is 0. So that's an option for doing it. But we can also work directly from the original form, and that would be important if this power were bigger, then this expansion would be hard, and also if this thing inside were particularly complicated or non-algebraic, then we would have a hard time doing that step. So we'd like to be able to work from the original expression. So the idea of the chain rule is to recognize that this function f of x is really a result of function composition. So what really this looks like is it's something squared where the something is a complicated expression. So we often call this inside part, we often call this part in parentheses, we call this the inside. And just for consistent with how we'll see it in Calc 2, I'm going to call this u. U is that expression inside, u equals 5x plus 3. And if we think of that inside as being 5x plus 3, then this function as a whole then could be written as u squared. So if I take this definition of u and then evaluate u squared by changing the u into 5x plus 3, that's exactly the function that I have. So really, this function f of x is really a composition of these two things. So when we can recognize that, and so like I said, we call the u part the inside function, and so correspondingly we'll call the outside function this u squared. Oh, that's big. So if I call that g of u to be able to reference it, then I have the inside function is 5x plus 3 and the outside function is u squared. And that's where we are here. So to compute the derivative, there's a rule that that's called the chain rule that will allow us to figure out the derivative of f of x based on the derivative of these two pieces, the outside part and the inside part. But what I wanted to show you in this video was where that rule comes from. And with most things in our calculus course, we always will start off with trying to understand how to approximate the idea of what we're doing, and then we see how to turn it into an algebraic formula. So I know this is a giant sea of equations here, but let's just work from the beginning. So first of all, the idea of a derivative is that it's the slope on the function f between 2 points. So for example, this is just a random example, but f prime of 2, for example, means the slope on the curve, this y equals f of x curve at x equals 2. And we can approximate that, and let's use this little symbol for approximately. I can approximate that by just doing a rise over run slope between 2 points close together, one of which is the x value 2. So I'm taking the x value 2, this is its corresponding y coordinate. I'm taking the point near 2, 2.001, and its corresponding y coordinate. And so this is literally the change in y coordinates over the change in x coordinates, or rise over run slope. So this is exactly saying that f prime of 2 is approximately the slope between 2 points in the curve close together, one of which is at x equals 2. Now, if we evaluate that, remember the function f up here is 5x plus 3 squared. And so evaluating at 2.01, I'd have 5 times 2.01 plus 3 squared. Evaluating at 2, I'll have 5 times 2 plus 3 squared. And I see I already have a typo. That's a record. The semester hasn't even started yet. But that's supposed to be 2's down there. And so if I simplify this expression, 5.2001 plus 3, that's 13.05. 5 times 2 plus 3 is 13. And so I get this. And now I do something that looks really weird. I'm taking this fraction, so this is a rise over run fraction, and I'm going to break it up into 2 parts multiplied together. These are equal just because this part and this part are identical. And so if you think about it algebraically, these would be canceling out and would leave me with just the numerator, 13.05 squared minus 13 squared, and the denominator, 2.001 minus 2. So the fact that these two guys come from here, it's easy to see those are the same. But why in the world would I do that? Well, and I can't get rid of it. Hang on. All right, let me erase this. The reason we would do that is because these individual fractions correspond to something in our inside and outside functions. Specifically, this first fraction here, this is the slope between 2 points on the curve g of u equals u squared at u equals 13. So if I take 2 points close together, 13 and 13.005 as inputs, then the output of that will be 13.05 squared minus 13 squared. So this is a slope on the g curve for values of u between 13 and 13.05. And so that means that this thing in the box is approximately the derivative of g at 13. So again, it's an approximation because the 2 points are just close together, but that's what it is. And then here, this also is a slope. This 13.05 minus 13 over 2.01 minus 2, this is a slope of the inside part. Remember, u is 5x plus 3. And so if you take the x values of 2.001 and 2 and plug them into this formula, you get 13.05 minus 13. So this is outputs, change in output over change in input for this function. And so we would denote that u prime at 2. And again, that's just an approximation. But it's a slope on the u curve at x equals 2. And so when we multiply those two things together, we're getting this approximation to f prime of 2. And so I'm going to write it up here where we can see it instead of at the bottom. We're getting that f prime of 2 is approximately g prime of 13, that's the outer function, the square function, times u prime of 2, and that's the inner function. So the only thing about that looks kind of weird is that 13 kind of pops up there. It makes you wonder what's going on because your original input is 2, and here this is u prime of 2, so that makes sense. But where the hell did 13 come from? Well, remember 13 is the result of putting 2 into u. And so ultimately we say this is g prime of u of 2. U of 2 is equal to 13 times u prime of 2. And so this is the chain rule in all of its glory. So that's not how we actually will compute things, of course. We want to compute as much as possible. We want to turn this into a sort of an easy algebraic process, but this is exactly why the chain rule works. So here it is again in all of its glory. And it looks a little hard to sort of parse when you write it like this because we've got, what, f, x, and u, and g. So there's 4 different symbols, and it's got some primes, and so it's a little hard to look at. So a lot of times what you'll see people write is they'll say, starting off with y equals u, where u is a function of x, In other words, u tells us a substitution like what the inside part is. If we think of it that way, then we'll say dy dx is equal to dy du times du dx. And that looks a lot more intuitive because it looks like these du's are canceling out in these fractions, which if you think about the previous slide, that's pretty much what was happening with our approximation. But even this, even though this looks a little more intuitive and looks easier to remember, it's still not 100% clear how that gives us back to this, this rule, and it's not clear that that makes it any easier to do. So I suggest, oh, I'm sorry, we're going to do an example to show how you would actually do it this way. Okay, so let me show you how you would do it using the chain rule as it's written, and then I'll show you an easier way to think about it. So the chain rule as it's written requires that we think about what these pieces are. So I would always start off with what looks like the inside part. That's usually pretty easy to identify. So we'll say the inside, we'll say the inside part here is x squared plus 1. And that means the outside part is what function of u would give us the original problem, and that would be this. So if you take g of u equal the square root of u and then substitute x squared plus 1 for u, you'll have exactly the problem that we're looking at. So if you have that initial setup, then I can say f prime of x is equal to g prime of u times u prime of x. And now I can just figure out what these two things are. Don't forget that square root of u is really just u to the 1/2. So we use our power rule for that, 1/2 u to the minus 1/2. So that's the derivative g prime of u. And then u prime of x, that's just the derivative of u with respect to x. And so the derivative of x squared is 2x, and the derivative of plus 1 is 0. So that's really the answer, but notice we have two variables in there now. We have a u and an x, and that's not really great for a final answer because there was no u in the problem, so it's not really fair to put a u in the answer. So we always have one more step, which is to replace u with what it's equal to, and that was our decision, right? We decided this. So u is really x squared plus 1, so I would change u into x squared plus 1, and then just copy the rest of it down. So this would be my derivative of the square root of x squared plus 1 using the chain rule. I think I do. Yeah, so if you want to pause and see it typed, that's the way it looks nicely written. What I would consider the simplified way of doing the chain rule is really acknowledging that when we're doing derivative rules, we really are only using a handful of elementary functions. So the square root function is one of the ones that we see a lot. That's really just x to a power. We also see sine and cosine and log and exponential functions. So if you think about the functions that we've ever seen derivative rules from, they really fit into just a handful of categories. So in some ways, you can make your life easier just by being familiar with what the chain rule looks like in each of those different situations. So for example, if the outside function is just raising to a power, which is what it was in the previous problem, it was the square root, which was raising to the 1/2 power, then we could just write down what the chain rule says in that specific case, and it would look like this. The reason that there's a little box in there is because the box is referring to the inside function u. But if we can remember the chain rule in this form, all we have to do is copy the same thing into each of those three boxes, and I have a true statement no matter what that thing is. So for example, if I have the derivative of the square root of x squared plus 1, like I had before, then it's going to look like this. I'm going to take my rule for the power, and here I'm thinking about the power being 1/2. And I'm going to write down exactly what that says, but I'm going to replace the boxes. Well, I guess I'm not really replacing the boxes. I'm going to fill in each box with the inside function, the x squared plus 1. And so that's what I have here. These two things, these two things are identical, where I've used 1/2 for my power, and I have copied x squared plus 1 into each of the three boxes. And so that's a very simple thing to do without having to think real hard about what the theory is saying. So if I copy the x squared plus 1 in each of the three boxes, and I always write this rule down. I don't try to do any of this in my head. This is literally what that rule says, and then it's telling me something to do. It's telling me that to finish this problem, I need to evaluate this. Right? That's still a prime there, so I need to do that part. So I just do that. Just the derivative of x squared plus 1 is 2x, and I'm done. You'll notice that a lot of times, well, I know in Calculus 1, a lot of times you would simplify this down so you didn't have these negative exponents and stuff like that. Personally, I would rather wait to see what I'm going to do with the answer before I simplify it. So, so from my point of view, typically this answer is fine. If I see a half times 2, I usually will do that. But I usually don't do a whole lot with it unless I know why I'm going to do something. In other words, if I have to solve it when it's equal to 0 or plug numbers into it or whatever, I would personally rather wait to see what I need to do with it before I just simplify it for no reason. But if you did want to simplify it, this is generally what you would try to simplify, is to get the negative exponent out of there and turn it back into a fraction. So bonus points for that. On these slides, I do have some problems to practice, and so these are all problems that practice using the rule for a power. Notice that the power differs here. So here it's the chain rule where the power is equal to 5. Here is the chain rule where the power is equal to a half, like we had before. And here it's a chain rule where the power is equal to -3. We'd want to rewrite that problem so that the exponent was -3 and there wasn't a fraction there. But if I just copy down the chain rule for powers in each of those three cases and fill in the box with the appropriate inside part, then it will work great. I'm not going to go through these. I have answers on here for you, so I would recommend you pause and try these and then compare them to my answers. Then if you want a little more practice, I have some more complicated ones that are mixing up having powers and chain rule problems, chain rule issues at the same time as having product and quotient rules. So there's 3 more problems that have more complicated answers. And again, pausing and trying them is not a bad idea. And then here are the answers. And again, if you try them, then just scroll back to here and check them out. By the way, all of the slides that I use for these videos do go up into the course website. So you don't have to write anything down. You can just download those files and follow along if you would prefer. So that's the benefit of having the chain rule specific to a problem that you're interested in or a function that you're working with. If we do the same thing to all of the functions that you would have encountered in a Calculus 1 course, it's a list of, what is that, 8 different rules in addition to the power rule. So in each case, what you're seeing is the box represents the inside part, and so what you're seeing in each case is the derivative rule for the outside times the derivative of the inside. So for example, this rule number 4, we know that when we take the derivative of e to a power, the rule for e to the x is, the derivative of e to the x is just e to the x, and so the derivative rule says don't do anything, but then the chain rule says, but you have to multiply by the derivative of the inside. Similarly, the rule for log of x, the derivative of log of x is 1 over x, so the derivative of log of something is 1 over that something, but again, it has to be multiplied by the derivative of the inside. So, so this is actually a pretty handy list to have available if you're doing chain rule problems, and after a while you start to see the similarity in all of them. We're always just using the derivative rule for the outside function times the derivative of the inside, and I think it's a little easier to do computations using the rules in this form.